All right, hello. Let's talk about what a database is at the highest level and about the data model that we'll be studying throughout the course, known as the relational model. So first, databases are ubiquitous. If you've interacted with any sort of software or service for which you have an account, you've almost certainly interacted with a database. Even software websites that don't have accounts, if they have a catalog, if if you can look through a collection of images, that's almost certainly stored in a database somewhere, because databases are simply a way of collecting real-world information and in some organized fashion that makes it easy to interact with, retrieve, analyze, things like that. There is a distinction between a database and a database management system. So a database management system is often abbreviated DBMS. And the database is the actual data, the files, whatever it is that is being stored. And the database management system is the software that is organizing, that is retrieving, that some user is interacting with in order to get access to the database. And this course, Database Systems, is going to be about how these management systems are actually designed and implemented. So let's think about how might we implement a very simple database management system. And if you yourself are implementing some small application, maybe for just a few people or a kind of convenience for yourself, it's unlikely that you would need to use one of these commercial database systems like IBM's DB2 or SQL Server from Microsoft or Oracle, or there are open source ones as well, Postgres, MySQL. We'll get into kind of this kaleidoscope of different database management systems later. But you might just want to keep some files around. Let's say CSV files. So you have a collection of CSV comma-separated value files. So you kind of have some strings separated by commas, and they're organized into kind of one kind of set of values per line of the file. This is how we're keeping track of our data. And our database management system is just some scripts that someone has written to interact with our comma-separated value files. Now, imagine that we were using this system for a database of student information here at Carleton. There would be some problems with this kind of simple, let's just keep some files around and write some Python scripts to process them. I mean, I think that all of you could, in Python or Java, write a script to read in a CSV file, parse apart the field separated by commas, extract some value from it. So we'd be able to do some things. But we'd have some challenges. So one major challenge would be redundancy and inconsistency. So we have these CSV files. Let's say there are some that keep track of student information for a particular department. So the math department and the music department both have kind of contact information for their current majors. This is something that they want to keep track of. But let's say, as is not uncommon, someone is a double major in both math and music. Well, now all the students' information is stored in the CSV file for the math department and the CSV file for the music department. And so we have this redundancy. We're keeping the same data around multiple times. This is going to require more storage, raise the cost of this database. But there's also an issue of inconsistency where, let's say that the students contact information changes. Their family has moved, or their phone number changes. Now, this might get updated in the files for the music department, but not the math department. So now our database has this inconsistency, and we don't have a kind of overall structure of software to keep everything consistent, to enforce anything. We just have some CSV files and some scripts. Another issue we run into is we might have difficulty accessing data. So let's say that someone now wants to, someone in the alumni relations office wants to find all the students who live in a particular zip code, maybe connecting students to local alumni, something like that. Now, unfortunately, the kind of existing, there is no existing script for, you can run a script and get all the students in a particular zip code. No one has kind of written that script. It's not sitting around anywhere. So, but there is a script to get the information for all students that includes the zip code. So a person in the alumni office now faces a problem where they can either run this script and get the information for all students and then manually kind of search through it and pull out the ones for the relevant zip code, or write a new script to get exactly the information they're looking for. And then if suddenly the requirements change slightly and, I need everyone who lives within 60 miles of this zip code, we again have to write a new script or manually pull out that information. And so we really want a kind of more consistent and structured way of accessing the data than this sort of what I'm going to call my flat file straw man approach to a database. Flat file meaning we just have a bunch of files sitting around and we're running scripts. Straw man is that this is kind of a motivating example for why we would need a more robust database management system. So there's other problems we might run into as well, things with data integrity. So if there's a mistake and someone's class year gets overwritten with some invalid value, it's not even a year, it's just some random letters, or it's a space, then there's nothing about this system that necessarily is going to catch that or enforce that, all right, in this database the class year needs to be a 4-digit number. If a student has multiple majors, how do we represent that in this flat file, this flat file approach? What if we want to create a new application that uses this database? There's no, because it's sort of ad hoc scripts and CSV files, it might be quite difficult to figure out how to integrate some new application with the database. As we'll talk a lot more about later in the term, there are issues of concurrency, meaning what if two threads, two programs try and modify the same file at the same time? We're going to have problems, and a real database management system will need to account for that possibility. There are security problems. If kind of all information about all students is in our database, it's not the case that every person, every college employee should have access to all of the data. We want to control that somehow. Folks in the business office don't need to know about medical things. Only certain people would need to know about that. So, but it would be hard to control that sort of access. It'd be hard to say, like, these users of our database have these permissions to access this certain amount of data, and so that's something that frequently in practice you will want to be able to do with a database system. And finally, we're going to have problems with potentially with durability. So if our computer system loses power while we're doing some update to our database. If we're just using kind of the standard ways of reading and writing files, there's not any infrastructure around this to ensure that this update is preserved, or there's some record of the fact that it was in progress when the system went down, and so we might just lose it entirely. So all this is to say that we want some sophisticated piece of software that's going to allow applications to store and analyze the data in our database. And we want a kind of general purpose database management system that's going to allow us to define our database, create data inside of it, query, ask questions about that data, update that data to modify it in various ways, and administer it. Things like controlling who has access to what. So, a bit of history. In the kind of early days of databases, and here I'm talking about kind of 1950s and 60s would be the early days, there was a kind of, we can think of database systems having kind of what I'll call a logical layer and a physical layer. And our physical layer is kind of the actual computer system that our database is running on. It's controlling kind of how and where data is stored. So in the previous example, the physical layer is those CSV files. That is what is controlling kind of how and where the student data was stored. And our logical layer is kind of logically which entities and attributes are stored in the database. So our logical layer is saying, all right, we're storing information about students. Students have majors. Departments have courses they offer. Courses have instructors. Kind of all these relationships. Kind of the kind of logical description of the data we're storing. That's this logical layer. Physical layer, how and where we're actually storing this on the system. And I bring this up because early in database systems, these two layers were tightly coupled. The logical layer was kind of intertwined with the physical layer in that kind of when we were describing which entities or kind of what operations are we wanted to perform with our database, it had to make kind of strong assumptions about the physical layer. And when you deployed a database system, you kind of had to know ahead of time, or you're only going to be able to support a kind of specific set of operations because you were kind of limited. The kind of logical things that you could do were limited by the details of the physical layer. This meant that if we wanted to change anything about the physical layer, then the logical layer had to kind of entirely change as well to fit this new physical layer. And so it was in 1970, a mustachioed British individual named Ted Codd proposed what is called the relational model. This went on to become the dominant data model for database management systems, and it specifically wanted to store our database in simple structures called relations. It's our relational model. Proposed to access database via some high-level language, so some way of interacting with the database that wasn't kind of at the nuts and bolts level of what was going on in the physical layer. And the physical storage was left up to the implementation, meaning that there would be this separation for kind of logically how things were stored in the database and how we interacted with them, and kind of the implementation of the physical storage would kind of support this common model of interacting with the database. Now, the relational model is not the only data model out there, and so I want to take, before diving deeper into the relational model, I want to take a brief detour through some other data models that are out there. So there's a set which includes key value model, graph data model, document, column family, and multi-value, and all of these are what is known as NoSQL models, which, as we'll get into starting next time, SQL, SQL is the kind of de facto standard language for interacting with database systems, and in particular ones that use the relational model. So there's this family of other data models that kind of originally kind of came out of, well, they're a different way, all sorts of different ways of representing data, but what they have in common is that they're not like the relational model. They don't support SQL as a way to access the data. There has been, over time, kind of a cross-pollination between these NoSQL models and the relational model. So relational databases have adopted some idea from NoSQL. A lot of NoSQL databases now support some amount of SQL, and so people now say that this stands for not only SQL. So there's been some kind of merging of these two in some respects. You might also use an array or matrix data model, and this is primarily for machine learning, ML, because the machine learning algorithms kind of want some set of often numeric or categorical features, and so these are typically represented as arrays or matrices. And if you ever used the scikit-learn or other machine learning tools in Python, those interact with kind of array or matrix libraries like NumPy or pandas, and so that's where that comes from. And then there are a couple others. Called hierarchical or network, and these are rare or obsolete. These are sort of precursors to the relational model, and have basically been entirely supplanted by the relational model. So kind of these are more a historical curiosity than the rest of these, which are definitely in use today. All right, so these we won't talk much about these alternative data models. Our focus in this course will be the relational model, definitely the most commonly used one, but I wanted to mention that these others do exist. All right, but we can do away with them now. Be gone. All right, so our relational model defines three concepts. these are structure, integrity, and manipulation. All right, so structure is the definition of the relations, of the way we're organizing the data, and this is the attributes that those relations have, kind of what properties are being stored in the database, and the values that we're storing for those properties, or rather the kind of range of values, the domain that those attributes can have. Integrity is ensuring that our database satisfies certain constraints. So these might include something like the value for the year attribute has to be a number. Would be an example of a kind of constraint that we'd want our database to ensure. And manipulation is how we're going to access and modify our data. So with these three concepts, we can kind of gives us a model for a robust database management system that is going to address a lot of the problems that came up when I was talking about a kind of flat file approach. So a few key terms. One is schema. And schema is the description of a particular collection of data. So our data model is this relational model, which is kind of this collection of concepts for how the database in general is going to work. And then a schema is our description of a particular data set. So kind of a schema would be the description of there are students and instructors and departments and courses in our database, and here are the properties that they have. A relation in our database is going to be an unordered set that contains the kind of attributes of that relation that represent specific entities. So we might have a instructor relation that has kind of is an unordered set of tuples, where each tuple is a value for kind of each attribute in that relation. So to make this a little more concrete, let's imagine that we have we have a database of music. Artists and albums and things like that, something that Spotify or another music service might want to maintain. And so we might have an artist relation that has a name for the artist, a year that artist started, a country that artist is from. And then, so that would be the relation. And the relation is an unordered set of tuples. And each tuple is a kind of row in our relation. And so we might, I don't know a lot about music. So let's say that we have an artist Big Brass Band got started 1972 in the USA. We have Banjo Explosion, creation of 1988 in the United States, and then a very avant-garde group, Sounds of Ice, started in 2018 in Iceland, as seems appropriate. And so we have our artist relation that has 3 tuples in it. And our artist relation is kind of defining right there as a name column, there's a year column, there's a country column. And then each row in this relation, each tuple, has kind of a value for each of the attributes that the relation defines. And the values for that the tuples had are typically what is called atomic or scalar, which means they're kind of they're not multi-part. They're a string, a number, true or false, something like that. They're not a list or some complex object with a bunch of kind of nested fields inside it. Though kind of modern databases can often support kind of non-scalar values. We're mainly going to be thinking in terms of the values in a tuple are going to be kind of self-contained. You may remember one of the data models I put up was multi-value. That's specifically a model about when you want to deal with data where kind of you're going to have a lot of nested data, things in lists, things like that. So our relation here, we would refer to kind of where n is the number of attributes. We'd say it's an n-ary relation. So this would be a 3-ary, or the arity of the relation would be 3. And kind of each attribute has a particular domain. So name is a string, year is a number, country maybe a string, or maybe we have some kind of special type that is like it's one of these certain country codes, something like that. And for all of these values, any of them could have the special value of null, representing that there's not a value for that particular attribute for that particular tuple. So in the relational model, I said that the relations were unordered sets, and this is important because a relation as a set means that it cannot have any duplicates. Every tuple in the relation needs to be unique, and there's this idea of something called a relation's primary key, which is the attribute or attributes that uniquely identifies every tuple in the relation. And in our artist relation here, you might say, well, name seems like it might be a reasonable choice for our primary key, right? We need to choose an attribute that is going to uniquely identify each tuple in our relation. But we could have, as unlikely as it seems, kind of multiple banjo explosions, multiple artists going by the name of Banjo Explosion. And so we might say our kind of primary key, our attributes that uniquely identify each tuple, can actually comprise multiple attributes. So we could say, okay, the name and the year together are going to uniquely identify every tuple, and that's probably going to work. Though who knows? Maybe there were 2 different Banjo Explosions in 1988. an exciting year in the banjo world. What is common in relations where there's not some necessarily rock solid choice for something that's going to be unique is a lot of database management systems will kind of automatically, if it is not provided, will automatically generate a kind of unique a unique attribute that's sort of just incremented for each tuple, and so we might have an ID of 1, 2, 3 kind of that's added to our relation in order to ensure that there is a primary key, there is some attribute that we can uniquely identify each tuple with. Now, there's kind of to look at an interesting kind of situation that will bring up another important concept. We might have, in addition to artists in our music database, we might have albums, and albums also might have a name and a year that they came out, and we might want to say, okay, artist, the albums are also produced by an artist, and so we might say that, well, there's Big Brass Sound, which was Big Brass Band's second album in 1974. And rather, we would not refer to the artist by name. We want to refer to it using the ID, because that's going to uniquely, that's guaranteed to uniquely identify one of the artists in our artist relation. So here we're seeing a value of having the primary key is if we want one relation to refer to another. We want to use something that's going to refer to a specific tuple in that relation, and so having our primary key be guaranteed to be unique for each tuple, that's what we want to use. So then we have a collaboration between Big Brass Band and Banjo Explosion. Big Brass Banjo. This was 1990, and here we have a bit of a pickle. We have an album that needs to refer, like there were multiple artists involved in this album, and we'd like to record that information in our database, but our artist attribute here isn't a list of things. It refers to a single tuple in our artist relation, and so this is going to be a big problem. If we have something like glacial tones in 2020 by our Sounds of Ice, that's going to be fine. Again, one artist, but we have this issue with our album that has multiple artists on it, and to solve this, we'll actually want to create a third relation, an artist album relation that is going to have an album ID and an artist ID. And so first we'll need to, instead of a instead of an artist in our album relation, we're going to want to do what we did for our artist relation and have an ID. And so we, again, can do 1, 2, 3, just something that's unique for each album. And then our artist album relation just contains tuples of album ID and artist ID. So we know that for album ID 1, that's artist 1. For album ID 2, well, one entry in this table would be for Big Brass Band, and another entry in the table would be for Banjo Explosion. So here we have tuples, we use multiple tuples to represent this multi-way relationship between, we have an album that is a collaboration between two artists, and so we have a relation that is kind of specifically including for each album all of the artists who were on it. And this is kind of how we would solve this problem of representing these kind of relationships in the relational model. And of course, our Glacial Tones album was by Sounds of Ice. So, couple questions now about this. First, what is we know that ID is our primary key for artist, and ID over here is our primary key for albums. I will note just by how this worked out, I drew ID at the end here, but typically the primary key is always listed first when you're writing out relations in a database. But in any case, what is our primary key for our artist-album relation? Well, we can see just by looking at them that, I will stop walking out of frame. We can see just by looking at them that our album ID and our artist ID are, they're not unique, either of these attributes. And so we're actually going to have our compound primary key, where it's both the album ID and the artist ID together form the primary key. And so any pair of these will uniquely identify a tuple in this relation. And the other important thing going on here is that this artist ID refers to the artist, a tuple in the artist relation, and the album ID refers to something in the albums relation, and this is what is called a foreign key relationship in our database, in that some attribute in this relation is actually the primary key of another relation. Hence the foreign key. It's a key, but in some other other relation. And this system of unique primary keys and foreign keys is how we represent all kinds of different relationships in our relational model. Okay, so that's the relational model. Let's now talk about how we would interact with it. Remember that we had structure. That's kind of how we're defining these relations. We had integrity. Things like, all right, we're gonna give our year attribute a type. It's going to have to be a number. We're going to give our name attribute a type. It's going to be a string. As well as constraints like, all right, we have a primary key that must be unique. And that every artist ID in our artist album must appear in our artist relation, right? This foreign key relationship says, all right, you can't ever have something, a value for this attribute that is not a value of ID in this relation. So that's another kind of constraint. And now we're kind of onto the third piece, manipulation. How would we access and modify our database? So goodbye, musical relations. And there are kind of two kind of categories, I guess, of what we'll call data manipulation languages, or DML, just to throw another abbreviation out there. And we can put these into procedural and non-procedural procedural buckets. And our procedural is our data manipulation is going to specify a high-level strategy. Let me just start that over. High-level strategy for a database management system to use. And so kind of if we're trying to retrieve some information from the database, our procedural language will allow us to kind of specify, right, here's at a high level the kind of strategy or plan to use in order to retrieve this information. And this is in contrast to our non-procedural, where we are only going to specify what data we want without indicating any sort of plan or strategy or order of operations for how to go about finding that. And this will kind of leave the creation of a plan, of a kind of set of operations, to the database management system itself. And as I'll get into at the end of this lesson, this non-procedural approach, which in fact is what the SQL language uses, is going to be very powerful. But it's built on a set of concepts that fall into this procedural category that I want to go over now. And these are sort of abstractions, a kind of abstract set of operations that you could apply to a database. So this kind of procedural language is called Relational Algebra, and it's a set of fundamental operations to kind of retrieve or manipulate tuples in our relational model. Kind of each operator that I'm going to discuss is going to take in one or more relations as arguments and produce a new relation as output. And we're actually going to be to kind of combine these operators together to create more kind of complex operations. So we have, first up is the select operator, which is going to take a relation and do some sort of filtering to produce a subset of the tuples in that relation. So let's get an example relation up here. I'll call it R. It's going to have an AID and a BID. Our AID is there's going to be A1, A2, A2, and A3, and our BID 101, 102, 103, and 104. So there's 4 tuples in here. And our select operator is going to be of the form sigma, and then it's going to have some predicate, which just means a expression that's true or false. and it's going to be applied to some relation. So, for example, we could say select where AID equals A2 from our relation R, and we could get out the tuples A2, 103 or A2, 102. Why are these in the other order? Because our relations are unordered sets, even though I have drawn them in a given order here, there's nothing about the relational model or the relational algebra that says they're in a specific order. And so this would be a kind of valid result to this select operator. We can also combine kind of predicates together with the sort of Boolean expressions that I'm sure you've seen other places where we're going to select where AID equals A2 and where BID is greater than 102. And for this one, we just get the A2 103 tuple is the only one where this predicate is true for the relation R. So that's select. We also have a projection operator, and it's going to use the I guess sigma starts with S for select. Our projection uses the capital pi as the notation, and projection is going to take a relation and outputs a relation with only the specified attributes. So selection is a way to select some subset of tuples from our relation. Projection is a way to select some subset of attributes of columns as I've drawn them here. But I'll say attributes just because I'm using attributes and tuples very intentionally, just because the terms like row and column can mean a lot of different things in different contexts. And when we're specifically talking about relational databases, tuple and attribute are kind of the most unambiguous terms that I can use. But projection is going to, we're going to have some, say A1, A2, and up to AN. You make these subscripts like they should be. On some relation, basically take this relation and then give me some set of the attributes of it. So and projection can not only select, projection can not only specify certain attributes, it can also rearrange the order that they're in and manipulate them as well. So let me show you what I mean by that. If we have our select operator from over here, where we're saying select where AID is A2 from R. As I said, we can chain these relational algebra operators together, and we can say, well, take this, the relation, which we've seen is these two tuples that come out of this operator, and project BID minus 100 AID of this result. And so, as I said, we're going to rearrange and also modify the attributes, and so this will give us 3 A2 and 2 A2 as our output, as our kind of output relation from this projection. So, kind of selection and projection are kind of core in terms of how we're going to access and manipulate tuples. Since our relations are sets, we also have a number of set set operations. We have union, intersection, difference, and product. I guess I'll leave off product for the moment. And so union is a kind of U-like symbol. It's not the letter U. It's kind of a math symbol. It's kind of a wide, uniform U shape. Intersection is that symbol upside down. Difference is just a minus sign. I guess I'll draw these with how they would appear. These are binary operators. So union, we would say R union S, and this says give all the tuples in R and all the tuples in S. And so you just get all the tuples from both relations in an output. However, for all of these, they require that the two relations involved have exactly the same attributes. That in our relational model, if we want to take all the tuples from R and all the tuples from some other relation S and kind of combine them into kind of all the tuples together, they need to have all the same attributes. Otherwise, it's kind of not a valid relation. It's kind of not grammatical from a relational model perspective. So union, all the tuples from both. Intersection, all the tuples which are present in both. So this would be the tuples that are in R and S, so it would just be those with the same values in both. And difference, if we said R difference S, it's all the tuples in R that are not in S. So we whatever tuples that are in R and also in S, those are kind of subtracted out, and we're left with whatever tuples are in R but are not in S. Then I said that we had product. This is another binary relation where we would say R cross or times S is how product would be written. And it says all possible combinations of tuples from the input relation. So if we had our relation S and it had an attribute snake, and the snake was, we had a big and a small as the values for snake, and we did R product S. This is going to give us a relation that has all possible combinations of the tuples from the two relations. So we'd have 8 tuples in total because for each it's all possible combinations. So we'd have big A1 101, big A2 102, big A3 103, A2 103, and big A3 104. And then we'd have these same for with small to get our all possible combinations. 2 small A2 103 and small 3 104. All right, so product is kind of a way to get this combination of two relations. And the last one that I'll talk about is one that we're going to hear a lot more about in the future, which is join, which has a sort of funky operator, kind of a bow tie sort of shape. So R join S, and we often might have some sort of, it's not predicate exactly, it's more of, maybe I'll call it theta, some sort of criteria by which this join takes place. And so what join will do is it's going to take in two relations, R and S, and it's going to output that all the, it's going to output a relation that's the combination of tuples where the attributes as defined by theta, or all attributes if we leave it off, are the same. So we a kind of a join might be if, say, we enhance our relation here that has I don't know, a plane attribute, and the plane can be big or small. Then we might write R join S, where I guess we'd say the first being plane equals snake S, and so this is joining the two together. So it's kind of the tuples from this product where the plane attribute equals the snake attribute. And so now that I've added this plane attribute here, we get big followed by with a 1, 101, big, and big, a 3, 104, big, right, where the tuples of this product where these two attributes are equal, and then the ones where small small matches up. And you might be thinking, the way I'm describing this actually sounds like what we're doing is we're selecting something with our criteria plane equals snake of the product of R and S, and that is in fact exactly what's happening in this situation. Is and we're seeing that we have an operator that can actually be expressed as a combination of other operators that we've discussed. That this join is selecting some subset of the tuples from the product based on some criteria. All right, so there are other relational operators. There's one for rename. There's one for assigning a kind of the results to a kind of temporary variable. There's an operator to eliminate duplicates. There's operators for aggregation, kind of maybe summing things up. There's an operator for sorting, so we can impose a sorted order on our unordered set. And there's also a kind of strange operator, division, which you're kind of getting out attributes that appear in one relation but not in another. I did want to note that in this join we kind of get the snake, rather the plane and the snake attributes twice. But you could eliminate that via a projection, right? You could use projection of this to only use kind of one of these or the other, so that it's not duplicated. All right. What I'd like to end with is observing the kind of procedural nature of this relational algebra. So, in particular, saying that select where BID equals 102 of R join S, we will actually get the same thing if we say R join, or let's say S join R. We'd get the same thing if we said S join select where BID equals 102 of R. So like this one is saying join S with R and then do the select, and this relational algebra expression is saying select some subset of tuples from R where BID is 102 and then join with S. So in this sense, relational algebra is kind of providing this high-level strategy. Like, here is the order of things that the database system should do in order to access the information in some way. And even though these two algebraic expressions will produce the same result, we're going to get the same relation out. There may actually be a significant difference in terms of their performance because if there's only, say, one tuple that has BID 102, if we select that first and then do the join, that might be a lot faster than doing a join if there's a billion tuples in R. Joining that with S might take a while, whereas if we select a single tuple out of R first and then do the join, that might be a lot faster. And so a better approach might be some way of interacting with the database system where we can just sort of describe what results we want. We can describe both, okay, we want it to be filtered by BID equals 102. We want there to be a join between S and R, but in a way that doesn't specify which order these happen in, the way that the relational algebra does. And then let the database system take a look at, because it's going to know things about S and R, and it can look and say, okay, which I could do this query in either order. Which of these two will actually be faster. And SQL is going to do exactly this, and that's why we're going to be spending the next two topics on it. All right. With that, I look forward to your questions about the relational model. I said with that, I look forward to your questions about the relational model. All right.